Today we're going to be talking about the chaos game, but before we can define that, we need to define recursion, because the chaos game depends entirely on recursion and iterative processes. Recursion is a topic we see utilized in mathematics and computer science with countless applications in both fields. In its most basic definition, it's a function that calls itself. If we expand upon that, we can see that the recursive algorithm is more of an approach to problem solving, specifically problems that are iterative or make progress towards a base case. In computer science, we see this explicitly in method calls and conditional statements. So if we look at the factorial n method, if you want to calculate, say, factorial 5, it would call itself over and over again, constantly making progress towards the base case, which is important because that guarantees that it will terminate. The base case here is if n equals 1, then you return 1, and then else it will return the number times the factorial of n minus 1. For example, if it was factorial of 5, then we would say it would be 5 times the factorial of 4, which is 4 times factorial of 3, etc. We can see this laid out explicitly in the method call. So it would say 5, then n minus 1 is 4, then n minus 1 is 3, etc., etc., until it comes to the base case where it would return 1, and then it would return 2 times 1, and then 3 times 2 times 1, and then 4 times 3 times 2 times 1, etc. Let's look at an example of recursion that doesn't rely on numbers. Let's take, for example, this equilateral triangle. This will be iteration 0. In iteration 1, we can draw another equilateral triangle on the inside to subdivide this original triangle into 4 subtriangles. If we take each subtriangle and repeat this process recursively, then in iterations 2 and 3, we can see that it makes progress towards the Serpinski triangle, which is an image that can be reproducible at any magnification or reduction.
So we've defined recursion. We need information from the past to calculate information from the future, and now we have the language that we need to talk about the chaos game and what that is. So follow me, please. We have a geometric construction. This is an equilateral triangle in the R cross R Cartesian plane, if you want to think about it like this. And I have 3 points defined, A, B, and C, with coordinates A1, A2, B1, B2. You get the point. So this is the algorithm that we are hinting at, the chaos game, and it has 3 steps. The first one, we pick a point, and this is arbitrary because I didn't say pick a certain point, just pick a point. 2, choose a random point. So you're either going to pick A, B, or C. And then the third step is you're going to draw the midpoint between what you picked and the random point. So as an example, I'm going to pick a random point. So camera woman, tell me when I'm good.
Good.
Right here. So notice there was no tricks here. It is actually truly random. And pick a B or C.
B.
So if we pick B, this is our point, and this is our randomly chosen point. The midpoint is going to lie on this line, and it's going to be about here. Okay? And the idea of recursion actually plays into here, because what we're going to do is we're going to feed step 3 right back into step 1. So this is going to be our new pick a point. So we're going to now use this. So pick another one. It can be B again because it's random.
C.
C. So now we use this new initializer point. Go to C, draw the midpoint. Okay, now give me 3 or 4, like A, B, C.
A, B, C, A.
A, B, C, A. Now, I'm pretty fast at drawing these, but a computer does it a lot faster. And we can actually generate 1 million points using this process. We render it out, and you're seeing what it's starting to look like. That's strange. You would think that something so random, chaotic, would just kind of maybe even fill in the entire triangle. That's what you might think. No. Are you seeing it? It's actually converging to the Serpinski triangle. And we can actually, the way we defined this when I coded this thing is I kind of used a for loop that looks like this. Instead of calculating factorial, it just says draw a point using those 3 rules. But because we did this, we can actually have parameters. So in this case, your parameter is n. I'm going to have 2 parameters in my function. We're going to have the parameter n, which actually symbolizes the number of vertices. So in this case, we have a triangle, A, B, and C. So in this case, n equals 3. And my second parameter, I call it hop distance, d. And that represents how far you're going when you jump. So for example, here we have midpoint. So hop distance would be 1/2, because you're going half the way between the points. But even though that's how I defined the chaos game, you can actually say, okay, I'm going to hop a third of the distance, a fourth of the distance. Or you can say n equals 4. So you use the same kind of idea, but instead of a triangle, we have A, B, C, D. And you should be seeing some results of what different n and d values look like. But now, what we need to talk about is the base case, the easiest thing that will help us explain everything else. Why is n equals 3, d equals 1/2? That's this Serpinski triangle thing we have. Why? Just why does it look like this? And it's going to tie into iterative function systems, and we're going to have Kerry talk about that.
So one of the ways that the chaos game is generated is by using the deterministic iterative function algorithm. What this means is that the chaos game would always be generated by a set rule. For example, if we create a chaos game with 3 points, and if we want to choose any points inside the triangle, the next point is going to be determined by this set equation right here, which is the midpoint between the point that we have chosen and one of the corners. For example, if we create a game with 1 point, t1 equals to 0, 0, and then t2 equals to 2, 4, and t3 equals to 0, 4, then the midpoint will always be determined by a set rule. When we choose a point within the triangle, let's say we choose point 2, 2, our next step would be to determine the where the output point is going to be. And let's just say we choose t1. So we will transform t1 by this equation. This will give us the point 1, 1, which is the midpoint between these 2 points. We choose, again, point 2, 2, and we want to transform the top corner t2. Then the top corner will be transformed by this equation here, and it will give us the output 2, 3. Now that we have covered the deterministic iterative function algorithm, Cal will tell us more about the chaos systems.
So we've already talked about recursive processes, iterative functions, and the chaos game itself. So I'm going to talk about the broader branch of mathematics behind the chaos game, which is the chaos theory. The chaos theory revolves around dynamical systems that are very focused on the initial conditions of the system. Initial conditions are of great importance in chaotic systems because even a small change in the initial conditions can change the outcome greatly. For example, a double rod pendulum is a very good example of this because even though it's a very simple system, any small change in the initial conditions can greatly change the outcome at the end. So I'm going to use the equation y equals x to show the difference between a chaotic system and a normal system that we're used to. So with a normal system or a deterministic system like y equals x, we have a starting position of 0, 0 and an end position of 5, 5, and then the path in between. If we change our initial conditions by adding 2, our equation becomes y equals x plus 2, and our end position, we can just add on the extra that we put on to the initial condition here, and get 5 plus 2 equals 7. So it's just our initial condition that we changed added on to the endpoint, and you can see the path is the same. But for a chaotic system, if you change the initial condition, your end position becomes totally different. So you wouldn't have the same path, it'd be entirely different, even though you just changed the initial position here. The double rod pendulum is an example of a chaotic system that is also somewhat deterministic. This is because the motion can be calculated with an equation, but because we have to round that equation at some point, even if it's to the 100th place, it'll eventually devolve into total chaos that we can't calculate. So we've talked about deterministic systems that we're used to, and also chaotic systems like the chaos game. So Johnny will talk about how chaotic systems can converge on something consistent.
So attractors are what dynamic systems tend towards, and it's what made them interesting in the first place. In the chaos game, for instance, it doesn't matter where you start, you'll always end up with the Serpinski triangle. So we can imagine variants of this chaos game. We see the one with 3 points. We can imagine one with 4 points with different factors, so how far the distance we're going. And also, a very famous one is one where you start with 2 triangles and you apply affine transformations to them with probabilities. And this will create a fern-shaped drawing. We say that the orbit of the seed is attracted to S, where S is the attractor. We'll briefly describe the Cantor set because it's an attractor of the 4-point chaos game. So the Cantor set is the bounded set from 0 to 1, and then at each iteration you take out the middle 1/3 of each of the intervals. So at this point we've taken the middle 1/3, and at the next point we've taken the 1/3 out of all of these two smaller intervals. And we do this infinitely many times, so we can imagine that the Cantor set is an uncountable set, but is also basically an empty set, except for at the endpoints. So when we look at the attractor of the 4-point chaos game, we see that it has some variant of the Cantor set. It doesn't necessarily take out the middle 1/3, but we see that the squares form and the middle intervals are taken out for each interval. So we saw that for our 3 and 4-point chaos games that we could describe the attractors with geometric shapes such as triangles and squares and their fractals of these shapes. Anything that deviates from this is called a strange attractor. For instance, the famous Mandelbrot set is composed out of like circles and like other weird shapes, and so we classify it as strange. The Mandelbrot set is basically the set of all complex numbers such that the sequence of this equation, of this nested equation, doesn't diverge. In this video we talked about the chaos game and the chaos theory behind it, and we talked a little bit about attractors and what these systems tend towards, and that concludes our video. Thanks.